All right, have your homework out if you would, please. Books open to page 79. You did problem 6, B and C, and you did problem 9. Before we take a look at the homework, though, let's review some things we've talked about recently. We've talked a lot about stress. From a physics definition, what is stress? Kendall? Deformative force per unit area. Very good. Force per unit area is pressure. Deformative force per unit area we call stress. What about strain? We've talked about that as well. What is strain, Michael?
It is. It's like the stress you can see.
It's the result of stress, generally. Depending on the rigidity of the solid. What is strain? If stress is the amount of deformative force per unit cross-sectional area, stress is what produces strain, but what is strain? The result of stress. Well, yeah, it's often true, usually true. Kendall? Okay, relative deformation. Relative deformation. Again, relative meaning not just how much deformation was there, but relative to what we had before. So if, the Inquisition came and got us all, and they put Kendall on the rack and they put Michael on the rack, and they stretched Michael out 2 inches, he might actually be like, oh, that feels good on my spine. That feels good, decompression. And Kendall's like ripped asunder with those 2 inches, and that's the end of Kendall as we knew her, and it's just sad. Okay? And somehow Audrey got out of it. It's got to be nice being in the middle, right? It's like short, tall, I'm just in the middle. He doesn't pick on me. We'll think of something for you. Believe me. You know, I've actually got the perfect thing coming up here in just a minute. We got this. We got Audrey. She's going down, literally. All right. As we talked about stress and strain, we said stress and strain are going to be proportional, just as stretch and tensile force are proportional, up to a point. There is a point at which the stretch and the stress and the strain, they're not proportional anymore. What do we call that maximum stress applied until the proportionality ceases to exist? Let's go back to Audrey. One might say this is the limit to which the proportionality can exist. The proportional limit, there we go. It's not creative names here. Then we had another point at which additional stress would permanently deform the object. So up to this point, the object can still recover its original shape. Past this point, no recovery. Well, not full recovery is not possible. The elastic limit. Then we had another point at which maximum stress, or you're going to break that object. Ultimate tensile strength. So you on the rack, right? What is the ultimate tensile strength? The maximum force before bad day. Shouldn't joke about that. That was a pretty awful time in history. And then there was another point at which we had the maximum strain the object could sustain. The actual maximum amount of stretch relative to the original size before the object would just break. And that was called the breaking point. So again, the big difference, ultimate tensile strength class is the max stress. If you want to think of it, okay, we don't know the cross-sectional area of the object, but the maximum force that can be applied before, okay, it breaks. You put too much force on it. Versus, you didn't necessarily have too much force, but it was on there so long, it continued to slowly stretch the object out till the object couldn't handle it anymore, and the molecular attraction wasn't strong enough, and it went ahead and broke. That's the breaking point. That's the max strain the object can sustain. Talked about 2 types of stress so far. 2 types of stress. Michael?
Physical and mental.
We didn't actually talk about mental stress because we don't believe in that. We believe God made you to handle. Okay, you can't actually get mentally stressed, but God did make you to handle the stresses that come in your life, right? You know, God isn't going to put more on you than you're able to handle through His help, right? Now, it isn't true, by the way, that God's not going to put more on you than you can handle. He will put more on you than you by yourself can handle to force you to rely upon Him, right? You think about things that Pastor Adam went through not that long ago, right? Without God's help, he doesn't make it through that situation. With your family, you've got some stresses, right? Through God's help, you're able to manage those. Without God's help, you might lose it, right? There's different things that God allows into your life to force dependence upon Him. And that's a good thing, right? We don't enjoy it, do we? we wouldn't pick it for ourselves, but if it teaches us to rely upon God and to realize we can trust Him even through circumstances like that, it's still a good thing. But anyway, no, that wasn't what the question was asking. Okay, we talked about, let me help you out here. One type of stress involved stretching or compressing. What do we call that?
Young's modulus.
Well, it uses Young's modulus, but the name for that type of stress is... Okay, there we go, tensile stress. He's like, well, if you're going to give it to a girl, I'll go and answer it. All right, tensile stress. The other type would be, for instance, if, this here is supporting very strongly, and then I started to pull down here. We've got the supporting here, and we've got me pulling here. So we've got opposing forces, but they're acting perpendicular to the length of the object. That would be called shear stress. So tensile stress and shear stress, the two types of stress that we looked at. Yeah, I'm about to say one of the, your homework question, number 9, which we're going to get to here in just a moment, involved hitting a nail, right? Have you ever bent a nail?
Yes.
Hammering the nail and you didn't hit it squarely and nail bends, you're like, oh, and you gotta rip the nail out and start over. It's really frustrating, especially if there's other guys around who are watching, you know. You want to look cool, like, yeah, I can hammer a nail too. And usually, the secret is instead of like trying to show off, just say, bam, and it's in. It's like tap, 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 get it set first, and then bam, and see if you can sink it with one blow. Girls, you ever hammered nails? You've bent nails before? Like, no, we're not like Michael. You've bent nail? Never bent nail? I'm not talking about these kind of nails. I'm talking like a metal nail with a hammer. Anyway, all right. So hammering nail. That'd be an example of shear, isn't it? Right? Because whatever the board is, or maybe it's a wall, you're hammering a nail into the wall, or whatever, right? That's the supporting force, and then the hammer, if it doesn't hit squarely, it comes at an angle or it comes downward, right? That produces that deformation. I thought of this example, Audrey. Okay, you've seen the cartoons, Bugs Bunny cartoons, right? Roadrunner, Wile E. Coyote, right? Inevitably, there's always a cliff somewhere in there. And let's say now it's Audrey, and she comes to the edge of the cliff, and you see the one with Yosemite Sam, it's like, or maybe it's Elmer Fudd, one of them, going to blast that wabbit, or whatever, and I was like, dare you cross that line, dare you cross that line, dare you cross that line, it crosses the line, falls over the edge of the cliff. Well, this time it's Audrey, and she knows no fear, so she falls over the edge of the cliff, but inevitably, what is jutting out of the side of the cliff just for Audrey? A tree branch, somehow jutting out the side of the cliff, and Audrey catches it as she falls. And the tree branch slowly begins to bend, and one finger at a time begins to lose grip, right in slow motion. And then there's this explosion at the bottom because if she has like this infinite mass or whatever. But anyway, what is that? That's shear stress, right? We've got the cliff supporting the branch. We've got the tree branch jutting out, and then there's Audrey hanging, and that's the shearing force bending the tree branch, right? So anyway, I told you it was going to end badly. She was going down. Anyway, her turn. All right. See, there's upside of being smaller. Tree branch would hold you longer. See? Yeah. All right. Anyway, we got a couple formulas. For tensile stress, stretching or compressing causes what? If you stretch something or compress something, what are you doing? You're changing the length of the object, right? So to find a change in length, what's my equation? Audrey?
X. Let's see. No, it's an F. Times L over A times Y.
There we go. And so that's for finding change in length. And then we had another equation to find the amount of deformation from shear stress. Very similar, but we're not finding a change in length. We're just finding how much does the tree branch bend as she hangs from it. And so how do we represent the amount of bend? It's not delta L, but rather class delta X. And we still have a force causing the deformation, right? It's just not a stretching or compressing force. It's a shearing force. And we aren't concerned about the original length of the object, but what are we concerned about? The distance. So in a perfect world, which cartoons never are, except that somehow she gets back up, shakes herself off, and all her hair grows back. Okay, that would be a coyote. Yeah. Something comes back. I don't know what it is. If it's a bird, all his feathers are gone, and then his feathers come back magically, or the fur is all gone on Sylvester, whatever. Somehow Audrey's back to her normal, lovely state after being this charred, singed mess. Anyway, but in a perfect world, when she catches the branch, instead of catching it at the end of the branch, she catches it right next to the cliff, because then less bend is produced, right? What goes here? Distance between the two forces, the distance between the supporting force of the cliff and the branch to which she clingeth. Okay? And the next thing we have in the denominator matches here, right? Still have stress, it's shear stress, so we still have a force per unit area, right? And the thicker the branch, the better her odds of survival. The thinner the branch, rest in pieces. All right, there and there and there. There's Audrey and there's Audrey. Anyway, I shouldn't be smiling about this, but she's smiling, so it makes me smile. Her lovely, radiant, smiling face makes me smile. I'm not actually happy about the idea of Audrey and Audrey and Audrey. All right. Anyway, but we didn't use Young's modulus. What did we use instead? The shear modulus, which wasn't named after anyone in particular, so it just S. And they think that been one of you who came up with this. You could have named it, Michael's modulus or something like that. M&M. Anyway, all right, so these were the two equations we were using. Although, remember for the homework on problem 6B and C, we didn't actually use this so much as we said that ultimate tensile strength or elastic limit is defined as force per unit area. I believe we were using this equation, the definition, if you will, of ultimate tensile strength and elastic limit, maximum stress. Force over area an object can sustain. Let's look at the homework now. And let's start with 6B. Go ahead and read problem 6, part B and part C for us, if you would. Michael?
An aluminum wire 6 meters long with a diameter of 1 millimeter hangs from a ceiling. If mass weighing 140 newtons hangs from the lower end, find or calculate the tension required to reach the elastic limit and the ultimate tensile strength.
All right, so we actually don't care about the weight that's hanging because it may or may not be sufficient to bring it to the elastic limit or ultimate tensile strength. It's only got 140 newtons. Question is, how much force would you need to get to either of those points? So the first thing we need to do is we recognize it's an aluminum wire. The fact that it's made of aluminum, as we flip back a few pages, tells us the elastic limit. So what is the elastic limit for aluminum, Michael?
2.7. Oh yeah, E10 or E8.
E8 pascals. So that's the elastic limit, and we know that's going to be equal to whatever force is necessary to get to that point per unit area. Now, what did they tell us about the cross-sectional area?
It's 1 millimeter.
1 millimeter in diameter. Okay, so the diameter is 1 millimeter, therefore the radius is 0.5 millimeters, or changing that to meters because Pascal involves meters squared. 0.0001205 meters. That value, that radius has to be squared and then multiplied by pi. So we're going to take pi times 0.0005 meters squared, and putting that over 1, we'll just multiply the extremes of the proportion to get the force needed. What did you get for the force required to get to the elastic limit? Michael? Why do I feel like we did this one already? Oh, I'm looking at the wrong answer in the answer key. I said, never mind. How much force is needed to get to the elastic limit?
I did something.
Uh-oh. I'm going to re-enter it. I would start with the squared value first. 0.0005 squared. Multiply that by pi, and then multiply that by the 2.78. Okay, and then round it off. I think it was just 2 sig figs in the problem, so we'll round to 210 newtons. So, 140 newtons that they had hanging there, that's not too far from the elastic limit, right? It's 2/3 of the way there. So they were getting close to that maximum stress before the object would be permanently deformed. And for ultimate tensile strength, what was that ultimate tensile strength for aluminum, Audrey? 3.18. Not a huge difference between the two of these. Let's see what it comes out to for forces now. Same thing, 0.0005 squared times pi times 3.18. How much force is needed to get to the ultimate tensile strength? Audrey? Yeah, 3.0005, then square that, times pi, times 3.18.
243.
Point.
47.
Once again, though, it's only 2 sig figs, so we'll say
240.
not a huge difference, right, in the force to bring to the elastic limit. Just 30 more newtons gets it to the ultimate tensile strength, meaning you go over 243, that 244th pound, or newton rather, excuse me, that 244th newton now would break it. All right, questions on that? Questions on the first part of the homework? All right, let's look at the next part of the homework, working with the shear stress, which we began looking at yesterday. Problem 9, read that for us if you would, Kendall.
How much deformation is produced in a millimeter picture now? 1.85 millimeters squared cross-sectional area. When the picture length 108 newtons is unfolded, the picture wire rests at the nail head, which is 4.10 millimeters from the wall.
All right, so here's the wall, okay, and we sink the nail in. Now, it's assumed, I believe, that the nail is sunk in horizontally. Strategy tip, generally speaking, it would be wise to sink them like this at an angle, so that way whatever is hanging will slide right up against the wall. As it does, what's the distance between the supporting force of the wall and the shearing force of the picture? 0, which means there's no shear produced, right? If you keep it level, there is a little bit of shear produced if the wire hangs, as it says here, at the nail head. So that tiny little bit of distance between wall and nail head, it says is 4 millimeters. That's the D. That's the distance between these forces here. But, well, actually, we can leave that millimeters, can't we? Just like we had the original length could be whatever unit, I can actually leave the 4 millimeters. I don't have to change that to meters necessarily. The force, we assume the wall can hold an infinite amount of force. Now, if it's sheetrock or drywall, that's not necessarily true. If you're into the stud, or if you're working into cinder block or something, you're going to have a lot more supporting force. But we'll assume the supporting force is infinite. What is the shearing force here, Kendall?
108 newtons.
108 newtons. That's the weight of the picture. All right? The cross-sectional area refers to the object that is being deformed, which is the picture nail. Does it give us the cross-sectional area?
1.85 millimeters squared.
Thoughts on the millimeters squared, class?
You gotta change it.
You gotta move that decimal how many places?
6.
6 places that way. What it's gonna produce then is a 1.85 e negative 6, because we moved the decimal 6 places, e negative 6 meters squared for our cross-section, or 0.0000185 meters squared, our cross-sectional area. And then we need the shear modulus. Well, again, as we look at the table, it said the nail was made of aluminum, so we're looking for the shear modulus of aluminum, Kendall.
2.6 E10.
Good. The 7.0, that's Young's modulus. That's if you were trying to stretch this nail. We're trying to shear the nail. It's easier to shear than it is to stretch. So 2.6 E10 pascals. Again, the meters squared and the newtons will cancel with the pascals, which is why we can leave millimeters up there. We go and plug in the numbers, and when you work it out, what do you get for the amount of bend in this picture nail? Kendall's recalculating. Audrey's recalculating. Michael feels confident in his calculation. Sort of confident. What'd you get, Michael?
9.0096.
And you went with meters here, didn't you?
Yes.
Yeah, okay, so yeah, 9.0 e negative 6 meters, or if you went with millimeters, 9.0 e negative 3 millimeters, or 0.0090 millimeters. Any of these answers would suffice. Good to go down, and good to go down. All right, questions on shearing stress, shear stress. So let's just say, for instance, let's actually analyze Audrey's precarious situation. Let's suppose she continues to hang it from branch, okay? So here's cliff, and jutting out of cliff is tree branch, okay? And Bugs Bunny eating carrot, okay? And Audrey hanging, okay? And so Audrey, she looks better in real life, I promise. And so does Bugs Bunny. Well, real life. Anyway, so we've got the tree branch. Now the first thing we need to know is how far from the cliff is Audrey hanging onto the branch. We'll let Kendall pick. Kendall's a good friend. Kendall, how far off the edge of the cliff is Audrey as she grabs the branch?
I don't want to be too mean.
We're not going to go 3 miles here, okay? It's not that long of a branch, okay? Actually, if it were that long of a branch, if she hung on long enough, it might just bend down and she could get down easily. Ah. So the shorter the distance, the more stranded she is. But let's go somewhat.
Probably like 3 miles away.
Yeah, somehow, she's like, ah! Gravity doesn't work that way. Pick something, Kendall.
I don't know, 50 feet.
50 feet.
Yeah.
So she falls off the cliff 50 feet away like that.
Yep.
So really what we have here is we have a cliff like
Yeah,
this,
like
and then
that.
here's the tree branch, and she's 50 feet away from the cliff. Okay, all right. All right, okay. Let's go with something maybe slightly more. Let's go 5 feet, okay? Let's go 5 feet, and that's about 60 centimeters. That's about 60 centimeters. So let's say she is 5 feet, 150 centimeters, excuse me. But 150 centimeters from the wall of the cliff where she grabs the branch. How thick is the branch you're clinging to? Now, Audrey, remember, you have to be able to grab it, so if it's this big, you're going to have a really hard time grabbing it. If it's this big, it's not very strong, so how thick is your tree branch? Diameter, give me a diameter.
Do half foot.
So about this thick tree branch.
Yeah.
Okay, so that's about 15 centimeter diameter branch. Okay, and we have to come up with a weight for Audrey. Now be careful, Michael, because you could be poisoned if you get this really wrong. Okay, so we're going to guesstimate Audrey's weight, and we're not going to get this really wrong.
Next question. I'm not answering this one.
All right, I will risk my life. I will say she's somewhere in the neighborhood, and you can confirm or deny, somewhere in the neighborhood of 110 pounds. In that neighborhood, give or take?
Yeah.
Okay, let's say she's about 110 pounds, which would be about 450 newtons. Okay, so we like pounds better than newtons for describing our weight. She's about 450 newtons. Okay, and let's see. The only other thing we need to know, this is wood. Okay, and we need to know, is wood on here?
Probably not.
Rats. Let's
Google.
see. Yeah, we need to Google this. What is the? I guess here's the question: what kind of tree branch is this? Is it like pine? Is it oak? Is it
Balsa wood.
balsa wood? Yeah, there's no hope. All right. Let's go with pine because we have a lot of pine trees around here. Shear modulus for pine.
According to MDPI, the obtained L-average modulus of shear is approximately 350 megapascals, while that of LR.
All right, 350 E6, that's 3.5 E8. All right, so 3.5 E8 pascals is the shear modulus. All right, at your seats. As Audrey hangs there, we're going to assume she has infinite grip. She is just going to last forever hanging there, at least until, some fire truck with a really long ladder gets up to her, unless, of course, like the ground's just right there. But if that were the case, she wouldn't care so much about holding on. How far will the tree branch bend? We've got the shear modulus, we have the distance from the wall of the cliff, we have the thickness of the tree branch, and we have Audrey's approximate weight. barely bends at all. No appreciable bend in this tree branch. What did you get for how much the branch will bend under your weight, Audrey?
3.4 meters.
It's not what I had. Either of you get that same answer? What did you have, Michael?
1.3 negative 5.
I didn't have that either. What did you have, Kendall?
I had around the same area as I did.
I didn't find the right area though.
Okay, yeah. So double checking your area, remember, we're going to need to do pi r squared. So this is radius 7.5 centimeters. That means 0.075 meter radius squared times pi. That's for your area. Go ahead and recalculate. And what do you have now, Audrey?
1.1 e-2.
And that's going to be in centimeters if you did it that way. If you change this to meters, you'd have 1.1 e negative 5 centimeters. Or meters, 1.1 e negative 5. 4.011 centimeters since it's e negative 2. So, I mean, 1/10 of a millimeter bend is all you'll see. That's a pretty strong branch right there. I mean, you know, it's got half a foot thickness. That's a pretty sturdy branch. Right? You've probably climbed trees on thinner branches before and been just fine. So that's more than strong enough. All right, questions on this? You understand how to use shear modulus and shear stress. All right, last section of notes as we wrap up chapter 5 today. Let's talk about volume stress. Volume stress. In parentheses, bulk stress. That's the old name for it. You might see that in physics textbooks at the next level. You might see if you were looking older texts, you know, as you're doing research for different things later on, you see a reference to bulk stress. That was the name I learned when I was in school. They now call it volume stress. Here's your definition. Volume stress is defined as compression over the entire surface of an object. It is compression over the entire surface of an object. Compression over the entire surface of an object. So it's not just getting squeezed like this in the Death Star trash compactor, okay? It would have to also be being squeezed downward and squeezed at angles and completely squished every little bit of you. For instance, if I took a ball in my hand, I could try to squeeze it, but the only places I would be applying force would be where my fingers touch and my hand touches, right? There would be places where it wasn't being squeezed. If you took a balloon, for instance, and squeezed it, right? Ever squeezed a balloon so hard that little things started popping through your fingers, right? And it started to stretch in those places. Every piece of the surface would have to be compressed at once. And there's really only one way this can happen. And that's if the object is submerged in a liquid. Because now the liquid literally covers every part of it, and that pressure is the same equally in all directions. So really what we're talking about with volume stress is only caused by objects that are submerged in liquids. For instance, the submarine that dives down to the bottom of the ocean and begins to spring a leak because it's being crushed so much under so much pressure. Or a diver who dives down deeper than maybe he should, or even if he's within his range, right? He still begins to feel that compression all over his body, correct? That's volume stress. Write this down. It's caused by liquid pressure. It's caused by liquid pressure. And always results in a negative change in volume. A negative change in volume. Kendall's like, that's what happened to me. I used to be 6 feet tall. I dove down too deep, okay? I was like this really fat girl who was really tall. And now I just got squished all over and I'm a skinny little short girl. See, that's what happened. No, because volume stress can't cause permanent deformation. As an object, as the diver resurfaces, he begins to expand back, if you will, to his original size. Not that the change in volume is an appreciable notice. He would feel it, but you really wouldn't be able to see any difference in the diver. Though, if he comes up too fast, right, that change in pressure can cause bubbles to form in the bloodstream, which can be very bad. Is that what they call the bends?
Yes.
Okay, I was about to say, it's been a while since I've done any research on that topic. Probably should have researched a little bit before talking about it. Anyway, these are the chances you take when you talk on YouTube. Anyway, but always results in a negative change of volume. So think about it. Remember, we'd always said, don't write this down, that F over A is proportional to the strain, right? The force per unit area is proportional, don't write this down yet, proportional to the strain. Well, in this case, we have the strain is relative deformation, right? Which is a change in the volume over the original volume, right? Just like change in length over original length. And that's going to be proportional to force per unit area. But think about it. Force per unit area is pressure. Deformative pressure, we call it stress, but really we could say that a change in pressure, or just in general pressure then, of the liquid is proportional to strain. But think about what pressure is for a liquid. Go back to chapter 3 now, the law of liquid pressure. Uh-oh. Did I mention we have a test coming up Friday that includes chapters 3 and 4? Rho GH, right? Rho G, and really it's the delta H that would produce everything. That's going to be proportional to or equal to this times a constant proportionality. We'll use bulk stress, or the bulk modulus, from the days of being called bulk stress, times the change in volume over original volume, but we have to have a negative change, so we'll say it's equal to negative bulk stress times change in volume over original volume. Taking this equation that's rather poorly written and crunched for space and solving it for the delta V, just as we solve for delta L or delta X, we'd say that delta V, here's what you do need to write down, is equal to rho G delta H times original volume all over the negative bulk modulus. It's the rho G delta H times the original volume over the negative bulk modulus, and that will give you the change in volume. Again, because of the negative bulk modulus, change in volume will always come out negative, meaning that this compression on the object as the object is submerged will result in a shrinking, a decrease in volume, a negative change in volume. Make sense? Let's look at an example problem here, page 77. Page 77. And look at the example problem at the bottom of the page, example 5.5. Read that for us if you would, Kendall.
Find the change in pressure at on 2.0
Cubic meter.
cubic meter latex balloon filled with water when it is poured 370 meters to the bottom of the Dead Sea. The density of the water in the Dead Sea is 1,240 kilograms per cubic meter. Find the water balloon's change in volume at the bottom of the Dead Sea. Ignore any effect of the latex in the balloon.
Yeah, so you know about the Dead Sea, right? Highly dense because of minerals and salt, especially other minerals as well, washed into the Dead Sea, and then there's no outlet. So it just sits there, and as water evaporates, the concentration just gets heavier and heavier and heavier. Fish can't live in it, nothing lives in it, hence the name Dead Sea. My science teacher in high school had the opportunity to go to Israel. Hans, I believe, are going to Israel, might be this summer if I'm not mistaken. And she had a chance to go to the Dead Sea, and they got a picture of her sitting on top of the Dead Sea. Not standing on it, granted, but sitting like with her feet up. So like if you sat down on the floor, didn't cross your legs, just sat down on the floor with your feet out in front of you, sitting on the Dead Sea, it's so dense it was holding her up. Only a small part of her actually submerged out into it. Greater density, greater buoyant force, right? So really, really dense. Well, if you pulled this balloon down to the bottom of the Dead Sea, high density liquid, what compression would it undergo? So again, we're going to take, again, this is just change in pressure, and the book uses change in pressure times original volume over negative bulk modulus, whatever. Well, pressure, again, is going to be the rho GH, right? So the density of the Dead Sea water class was 1,240 kilograms per cubic meter. Technically, G would be a little stronger there, more like 9.81, I think probably 9.81, maybe 9.82, I'm thinking 9.81, but let's just say 9.80 since that's a consistent value we opt to use. And pulled to the bottom of the Dead Sea. So what is that depth or change in height, so to speak, to which the water balloon was pulled?
370 meters.
370 meters down to the bottom of the Dead Sea. And the original volume of this water balloon was 2 cubic meters. All right, so there's the original volume. By the way, whatever the unit of the original volume is the unit for the change in volume as well. Okay? And then we need the negative bulk modulus. Well, the latex itself isn't being compressed. The latex itself is simply holding the water in. It is the water that is being compressed. So flip back a few pages. And let's look at water. Now, water cannot be stretched, so there isn't a Young's modulus. Water cannot be bent, so there is not a shear modulus. But water can be compressed slightly. What is the bulk modulus for water? 0.21 E10 pascals. By the way, note that the pascals in the bulk modulus cancel with the pascals from the pressure. So whatever the units are here, as I said, will be here. Go ahead and plug that into the calculator. We drag this 2 cubic meter water balloon to the bottom of the Dead Sea. What will be the change in volume? And what do we get for the change in volume, class?
Negative 4.3.
Yeah, negative 0.0043 cubic meters. Not much compression at all. Did it say to find the new volume of the balloon, or did it just say to find the change in volume? It is to find the water balloon's change in volume. Okay? Very little change in volume. Now there is some, right? Now remember we said an ideal liquid is incompressible, right? Water is compressible. The water was compressed, okay, slightly, not much. It's nearly an ideal liquid, but there is some compressibility to it. Questions on that? All right, look at page 79 now. Page 79, let's look at problem 11. And read this one for us, Audrey.
If a steel anchor whose volume is 450 cubic centimeters at relative depth of 1.5 kilometers of seawater, by how much does the volume decrease? Assume the density of seawater is 1,030 kilograms per cubic meter.
All right, so we're finding the change in volume. And my equation here for change in volume, class?
Rho GH.
You could say change in pressure, that's fine. Rho GH times V sub O over negative B. But this is called the bulk modulus. So we have the Young's modulus. Shear modulus wasn't named after anyone, and bulk modulus also was not named after anyone. Okay, for the record. So we plug in some numbers here. The change in pressure for this anchor as it goes down to the bottom of the sea here. We have the density of seawater.
1,030 kilograms per cubic meter.
Good. Gravity, now again, gravity is going to be stronger the deeper you go. So, one could again argue maybe the 9.81, 9.82. We're just going to roll with 9.80 for consistency's sake, though. And then the height or the depth.
1.5 kilometers.
That needs to be changed to meters. Because remember, the pressure right here needs to be in pascals, so we need meters. So,
0.001.
ooh, careful.
1,500.
1,500. You're going from an E3 to an E0, so the E is going down. That's downright good. Move the decimal right 3 places, 1,500 meters. And then the original volume of this steel anchor. 450 cubic centimeters. And I would not want to have to do the math to figure out that volume. You know the easy way to figure out the volume though, right? You'd take a full container, drop it in, allow the overflow to be captured by something else, and then calculate the volume of the captured liquid. Right? That would give you the volume of the anchor rather than trying to do some sort of calculation on it. And then the negative bulk modulus. This is steel that's being compressed. What is the bulk modulus for steel?
16.
All right, and at your seats, go ahead and plug in those numbers. And what is the change in volume of the steel anchor? Kendall?
-0.0425.
There we go. And so we'll round that off. 2 sig figs? Getting it? Yep. All right, so we get and we're going to go with whatever units we have here, which is that cubic centimeters. Again, not much compression at all, but it is still there, right? Slightly compressed. Again, as you pull the anchor up, it'll be able to expand as the deep pressure decreases again, so you won't notice the change in pressure, or the change in volume, right? There's not an elastic limit or anything where it's never going to recover its original shape. No, it'll expand back. Questions on this? All right, any questions at all on volume stress or shear stress? Questions on this? All right, tomorrow we are going to have a quiz over chapter 5, and of course got your test coming up. That's going to be in lesson 34. That test will cover chapters 3, 4, and 5. We've already tested chapters 3 and 4. Okay, there's just going to be a little bit of review over those. The emphasis of this test will be chapter 5. Really, the curriculum only calls for a test over these 3 chapters, but I've found that if I don't test 3 and 4, students forget a lot of that as we get into chapter 5. So hopefully that other test will help retention. Also allows me to focus more on chapter 5 on this one. All right. Have a wonderful day, and you are dismissed when the bell rings.